For number 10, it says, what is the wavelength of the radiant energy emitted when an electron in a hydrogen atom falls from n equals 5 down to n equals 2? So when electrons are excited and they fall from some higher energy level, in this case it's just 4 to 1, but no matter how it falls, so from 5 to 2, it's going to release a photon of energy. And that photon of energy is going to have a certain wavelength. Maybe a color, maybe not a color. You know, the electromagnetic spectrum is continuous, but energy levels are quantized. So when an electron falls from one energy level to another, it's going to release a photon of energy. Now, in this case, you're falling from N5 to N2, so we know it's going to be a release of energy, not an absorption. There are two equations that are often confused, but in reality, they're the same equation. So one equation relates wavelength with the energy level change, and then another equation relates the change in energy with the energy level change. In this case, we actually are looking for the wavelength, so we don't need this one. But if you were curious, this equation can be derived or turned into this equation. If you remember that E equals hc over lambda, and hc is actually just a constant. So the three things that I have circled here, R, H, and C, the way that the math works out, R is a constant, H is a constant, C is a constant. E and lambda are variables, and with algebra, you can actually see the relationship between this equation and that equation, but we don't need to look into that right now. Which equation do you use is the main practical question people are going to want to know. So I will save this equation for later, move it away. We are looking for lambda, which is wavelength. R is this constant, the Rydberg constant, about 1.1 times 10 to the 7th inverse meters. And then we have, the equation can get a little weird because depending on where you look, sometimes it's n2 over, n squared 2 minus n squared 1, or maybe it's 1 and 2. Final minus initial is actually probably the easier way to look at it in this case. All right, so all you got to do is plug everything in. So let's do that. We have 5 as the initial energy level. So you can put a 5 here, and we're squaring that. So that's going to be 25 in the denominator. And then 2 is the final energy level. 2 squared is 4. So we can replace that here. And then R is that number. Oops. So, okay, what's going on there? Oh, I'm not in eraser mode. There we go. So if you move this over and then just put that number here, then you'll get an answer that is tempting. But just remember, struggling. Okay, there we go. But just remember that when you get your answer, you'll have 1 over lambda. So doing the math, let's actually do it. So 1.1 times 10 to the 7. I'm multiplying that by the inverse of 4. Subtract away the inverse of 25. Delete. Oof, okay, hold on. This is a mess on my calculator right now. There we go. I get a big number. Now, this big number is 1 over the wavelength. So it's like 2.31, let's see, 1, 2, 3, 4, 5, 6. So 2.31 times 10 to the 6th. And this is actually not your final answer because you still have to invert this. And then once you invert it, so if you invert both sides, then you'll get the wavelength is equal to 4.32, say 4.33 times 10 to the negative 7 meters. And you're looking at your answers and you're like, oh yeah, he said like in the last part or the other last part that you're supposed to convert your meters into nanometers. So to do that, I'm just going to multiply by a billion, so that's 1 times 10 to the 9th. So multiply by 1 times 10 to the 9, and that's how you get a reasonable number of 433 nanometers. The reason that you're not using this equation is because you're not asked for the change in energy. You're asked for the wavelength. Now, theoretically, you could take this wavelength and then plug it in to the equation that relates energy, Planck's constant, speed of light, and wavelength. So if you plug this into here, you could get the change in energy if you wanted to. That's just the way the math works, but you don't have to. Just recognize those two equations and when to use them. Let's take a look at number 11. It says the element polonium has 84 electrons. So if we go ahead and find polonium, it's right here. It resides in the p block. Now it's in the 6th. It resides itself within n equals 6. But remember that any element, according to the alpha principle, will still have all the levels below it as well. So although polonium resides in n equals 6, it also has the n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. So that means that although we're looking at polonium, which is n equals 6, it actually contains all the electrons in here as well. So it says how many of these electrons have the quantum numbers n equals 5. That means it's something over in here. And L equals 1. As we saw way back up here, we said that L tells you how many, or which, I guess I say like which orbital it is. So L is going to correspond to the p block. So you're looking at the p block, which we clearly see is 6 elements wide. It can hold a max of 6 electrons. So if you see L equals 1, that really just means find the p block and then go to the 5th level of the p block because it says n equals 5. So scroll way back down. Whoops. And to kind of parse this, let's see what it's talking about. N equals 5 refers to, I'm going to change the color up and do this. That refers to this whole section here. Pretend like that pink isn't there. If I erase the pink, it might erase the whole picture. Sometimes it's weird. So n equals 5 refers to this. So I'm going to get rid of this part here. Okay. Now that we know that n equals 5, based on the question, we're like, okay, which part of n equals 5? Oh, yeah. The L equals 1 part tells us it's the p block. So that means it's actually this part of it. And you can just count and see that it's 1, 2, 3, 4, 5, 6. All the electrons in that area are going to have this part of they're going to share this part of their quantum numbers. They're all going to be n equals 5 because they're in, the 5th principal the 5th energy level. And they're all going to be L equals 1 because they're in the p block of n equals 5. So there's 6 possible ones. Every time you add a quantum number, you get more specific. So that's why it's a relatively large number at 6. If they had added like m subscript L, that would cut the numbers down even more. And then if they added even m subscript S, then that would be like a positive half or a negative half, and that would give you just one single electron. But there are actually 6 electrons that fit the criteria of being in the 5th level. So that's all of these. And they're in the p block. It's very important, and I'll write it again, that you recognize that S, P, D, and F correspond to certain L's, which really is like a landmark in my opinion. L equals 0 for S, L equals 1 for P, L equals 2 for D, and L equals 3 for F. That kind of narrows it down as well, a lot. This one. Which of the following species are isoelectronic? Iso means same or one, and electronic refers to the electronic structure, so the same number of electrons. It's very tempting for people to be like, oh, zinc, zirconium, like you're looking at these and you're looking at just the closest ones. It's helpful, but it's not totally safe. So let's actually take a look at how you would answer this question. Which of them are isoelectronic? I am going to paste the periodic table again because it's very helpful. Let's see. Okay, so when something is isoelectronic, that means it has the same electron configuration. I'm going to show a quick example. Let's do neon. Normal neutral neon is 1s2, 2s2, 2p6, and that's it. That's what neon is all the time. Now, what is oxygen normally? Normal oxygen, I guess I'll write this is neon. Whoops. Oh, this is normal neutral neon. Let's see what regular old normal oxygen is. Normal oxygen would be 1s2, 2s2, 2p, 1, 2, 3, 4. That's normal oxygen. But what if this were an oxide anion, so it gains 2 electrons? If I make this not neutral oxygen like it is right now, but if I make this O with a 2 minus, I'm going to add 2 electrons. And now it's 2p6. Notice how these have the same electron configuration. These are considered to be isoelectronic to each other. They're not the same element, but they do have the same number of electrons because this oxygen gained 2. Let's take a look at, so I did oxygen and how it's isoelectronic to neon when it gains 2. What about if I have, let's say, sodium? Normal neutral sodium is 1s2, 2s2, 2p6, 3s1. However, if I make this a sodium ion, so a sodium cation, it loses 1 electron. It actually loses the electron from the 3s, and that goes away. And it turns out that actually all 3 of these species are isoelectronic to themselves. So if you can write out the electron configuration, just remember if electrons are coming or going, it will affect your electron configuration. All that to say that your job is to figure out which of these are isoelectronic. Here's a trick. Find the number of protons, which is also the nuclear charge, and then add or subtract the number, and assume that it's neutral to start, and then add or subtract electrons to figure out how many electrons it will have. So here's what that means in this example with the simpler stuff. So we know these are isoelectronic. I'm going to revert these back to their originals. So let's make that neutral. This was 3s1 and this was 2p4. So right now they're not isoelectronic. These are the neutral versions. Now let's count up a number of protons in neon. Protons in neon is 10. That means that if it's neutral, it'll also have 10 electrons. So let's say that neutral neon has 10 electrons. Neutral oxygen has 8 electrons. And then neutral sodium has 11 electrons. To get the same number of electrons, they're going to have to lose or gain. So if oxygen gains 2 electrons, so plus 2 electrons, that's going to give you 10. Oh, look. The same as neon always has. Neon is a noble gas. Things tend to become isoelectronic to noble gases. Noble gases are like the stable ones. They don't gain or lose really electrons. So far we see how oxygen would become isoelectronic. It would become a 6 here. It gains 2. So that's one way you can do it really quickly without even doing the electron configurations. Is just count them. We added 2 electrons to oxygen, and now it has the oxide ion has 10, just like neon always does. Sodium normally has 11 electrons, but if the sodium loses, let's change it to red. If sodium loses an electron, it'll be the Na plus ion, which means that this thing goes away. But if you were to just kind of do it counting-wise, you're subtracting 1 electron, and that's going to give you 11 minus 1 is 10 electrons. So far we see that these are all isoelectronic simply by counting. So how does that work for this problem? So we're going to look for our noble gas. I would recommend if you get a problem like this, find the noble gas. Krypton is the noble gas. Things tend to become isoelectronic to noble gases. Find krypton, and you'll see that krypton has 36 electrons when it's neutral. So then you kind of look at the other elements. Zinc has 30 electrons when it's neutral, right? But you lost 2, so minus 2, and that gives you 28. That's not looking like it's going to fit into the zinc. It's not going to give us the same number of electrons as krypton. So zinc 2 plus is out. Now let's take a look at zirconium. Zirconium normally has, where is it? There it is. Zirconium normally has 40 electrons when it's neutral. So we're going to put a 40 up here to do our counting. But this zirconium has lost 4 electrons. So we're going to subtract 4, and that's going to give us 36. So far, zirconium's looking good because the 40 it normally has, but then it lost 4 based on that charge, and that gives us 36, which is the same as krypton always has. Let's find bromine. Bromine has 35 electrons when it's neutral in order to match the 35 protons it always has. And this is a neutral bromine, so you're not gaining or losing. This bromine will have 35 electrons. It didn't lose or gain any. So this is actually not isoelectronic. So we're going to cross that out as well. This is selenium. I'm going to shrink this down. This, I'll put a star under it or above it. That krypton is like our base level. It's our noble gas that we're seeing what's isoelectronic to it. Selenium. Selenium normally has, 34 protons. So when it's neutral, it will have 34 electrons as well. So let's write that, 34 for the selenium. But the selenium has gained 2 electrons. So we're going to add 2, and that's going to give us 36. That's looking good. That means that the selenium ion, the selenide ion, is isoelectronic to the krypton, which was this is like our base reference. So far we have 36 over there, we have a 36 here. Iodide. The iodide ion, neutral iodine has 53. Now, that's already seen me like it's way too far from 36. But anyways, keeping on with the pattern of problem solving, it's 53. We gain 1. And it's going to give us 54, which is just not the vibes. So cross that out. Rubidium, rubidium, is 37 normally. So that's going to be 37 protons, therefore it's going to have 37 electrons when it's neutral. Now we are losing 1 electron, so that's going to give us 36. That's looking good as well. Calcium normally is 20. That's pretty far from 36, so that's not looking good. And then we're adding 2 electrons, or we're subtracting 2 electrons, not enough. So it's 20 electrons. Subtract away 2, because it lost 2, and you're going to get 18, which is just too far away. It's also just not, it doesn't work. And then we have niobium, I believe it is, Nb. Where is that? Nb is over here. It's 41. Now, 41 electrons, but then we're going to lose 3 of them. So minus 3, and we're going to get 38, which is not 36, so it's also not going to fit. So what actually survives? What's isoelectronic to krypton is going to be the zirconium 4+, the selenium 2-, the rubidium 1+, and of course the krypton itself, because all of them have 36. So that's how you do it with counting. So hopefully that kind of clears up what it means to be isoelectronic. You can do the electron configuration, which is kind of extra, or you can just kind of count based on the neutral number and then add or subtract. So which of the following species are paramagnetic? For this one, I would recommend you actually write out the orbital diagrams. So these notes make it kind of self-explanatory in the sense that paramagnetic just means that there are some unpaired electrons. So we have some unpaired electrons as opposed to diamagnetic, where we have paired electrons, all paired electrons. So the reason that once you know the definition of paramagnetic and diamagnetic, then you're going to be tasked with determining which of these is paramagnetic, or maybe your question on the test will be which of these are diamagnetic. It doesn't matter which, just know the difference between para and di. After you know the difference, you need to remember the electron filling rules. In this case, it's going to be Hund's rule, along with a little bit of Pauli exclusion principle. So let's actually do that for iodide. So 1s2, 2s, you have 2p, oops, you have 3s, 3p. I'm going to write these out. It's kind of tricky remembering it all from scratch. So 1s2, 2s2, 2p6, 3s2, 3p. I need to look at the periodic table. Believe it or not, I don't have it memorized. I have a lot of it memorized. Let's see. Iodide is, whoa, God, iodide's kind of far. Okay, we can make it work. 3p, 4s. And I'll write this out. We can actually reuse it. After 4s, you get the D. So it's 1, 2, 3, 4, 5. And then you get P again. I'm going to do our 4 P's right here. And then we have 2, 3, 4, 5s. Okay, maybe you don't have to write it all out. I'll do that for the purposes of you kind of seeing how it works. We have 3D. Oh, we're almost there. Okay. We have our 4D. And then we finally are at our last part, which is P. 2, 3, 4, 5. Thank goodness. 1, 2, 3. So this is our 5P. All right. Now, if we were to do the iodide ion, I guess I'll write out the electron configuration too, which is a little bit of a hike. But let's use the abbreviated form. So iodide is here, which means we'd use krypton for our abbreviation. Whoops. So I'll do that in purple. So krypton, and then after what changes after krypton is 5s2. And then we have 4d10. And then 2, 3, 4, 5s or 5p5. Okay, that's a lot. But luckily, the thing is that's really helpful about the abbreviated form is that we know it's just a bunch of filled in things. So I'm going to pause it and just fill in all the arrows until we get to krypton, and then we'll fill them in according to Aufbau and Hun's and all that. Okay, I would like to say that took forever, but I just, copy and pasted a bunch of my own arrows in. So we have all the electrons filled in up to what represents krypton. Now let's go for what's new, which is all of this stuff. I guess I'll color code this, is all the krypton things. What's new since krypton? We have up, it's not red. You have up, down, that's 5s2, 4d10, so 1, 2, 3, 4, 5. What you're seeing me do is Hun's rule, which says you put all the ups in and then you go back and do the downs. Now 4D is a completely filled level, so that's what that looks like. And then you have 1, 2, 3, 4, 5. That's what iodine looks like if it were neutral. But remember, this is an iodide, so it added an extra electron. So we're going to take that 5, turn it into a 6, and that means we're going to complete this level. Iodide, as you can see here, has no unpaired, the iodide ion has no unpaired electrons. So you would say that the iodide ion is diamagnetic. So I guess I can go up here, put a D for diamagnetic. And then as a trick, kind of speed this up for you, if something assumes the electron configuration of a noble gas, then it's considered to be diamagnetic because all the noble gases are diamagnetic. They don't have any unpaired electrons. So this iodide ion assumes the same noble gas configuration, or it is isoelectronic to, where is it? Xenon. So I'm going to say isoelectronic to xenon. So if something is a noble gas, or if it assumes the electron configuration of a noble gas, if it loses or gains electrons, so it's isoelectronic, then it's going to be diamagnetic, not paramagnetic. So that makes iodide diamagnetic. Magnesium, if you were to, let's see, I'm just going to highlight all of what, we have so many electrons on the screen now, it's actually helpful, I think, to just kind of highlight it. So what would magnesium be? Magnesium completes the 3s2. So magnesium is actually just all this stuff right here. So if I were to write out just the orbital diagram for magnesium, it'd be all this stuff, and therefore the electron configuration would be 1s2, 2s2, 2p6, 3s2. We clearly see that if we limit our scope to looking just at what magnesium is, it is going to be diamagnetic as well. What about the chlorine? Neutral chlorine. So let's expand that. I'm going to highlight what makes chlorine now. Chlorine is not completely at the end of the 3p. So chlorine would be this stuff. I will edit it. Hold on, make it different now. If I were to do chlorine, it would look like this. Ignore all the stuff that's not in yellow. So all this right here, all the yellow stuff is currently chlorine, a neutral chlorine. Now we see here that there is one unpaired electron, so that would actually make chlorine paramagnetic. If it were the chloride ion, it would be diamagnetic, but the chlorine, as it is neutral, is paramagnetic because it has an unpaired electron. Let's continue on with sulfur. Sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. So actually, sulfur is one less than chlorine. So it would look like this. Sulfur is very clearly, actually, let me fill it in. So this is what sulfur would look like. Sulfur is very clearly paramagnetic. And then you have the phosphide ion. So phosphorus is even one to the left of sulfur, but since it gains 3 electrons, it's actually gonna, so this is what, okay, let me back up and say this. This is what sulfur would look like normally. Pure neutral phosphorus, I should say phosphorus. So phosphorus would be this. It would be very clearly paramagnetic if it were neutral phosphorus. But notice how this phosphide ion gains 3 electrons. So since it gains 3 electrons, it's actually going to look like this. And that would represent phosphorus, 1s2, 2s2, 2p6, 3s2, 3p6. That represents the phosphide ion. So therefore, the phosphide ion is also diamagnetic. So the only 2 paramagnetic ones are chlorine and sulfur, because if you do their electron configuration, their orbital diagrams, they will have some unpaired electrons.